I'm still better today.
Okay, welcome everybody. Thanks for coming. So today it's my pleasure to introduce the other organizer of the avalanches, one of the other organizers. She wanted to introduce herself, but I told her that no, it's not going to happen. So it is my pleasure to introduce Yuanyuan today.
Doctor.
Oh, Dr. Yuanyuan. So look better if she is there. So Yuanyuan is a new postdoc here. Before she came here, she did her PhD thesis at the University of Alabama with Dr. Jimmy Irwin. After that, she did a postdoc at the University of California, Irvine, with David Biot. And after that, and last year, so it was October or September, when did you, August, you came in August, I think. So last August, she joined us. Since then, she has been very busy, and she's working mostly on X-ray data, and she is the proud PI of 15 Chandra Experiment Suzaku proposals. Okay, and today she's gonna talk us about something which she has been working on in the past almost half a year now. So please.
Thank you. That was a very nice introduction. The highest point in Texas, and so the clouds pattern you see here, they are formed when you have two different kinds of fluids when they have a relative velocity to each other, and we expect to observe this Kelvin-Helmholtz instability at the interface between those two kinds of fluids, and the intercluster medium is made up with highly ionized hot gas. And such hot gas is emitting strongly in X-ray. And such cluster hot gas can also be regarded as plasma. And so exactly the same physics should apply to the intercluster medium as well. And galaxy clusters are formed at the nodes of the filamentary structures, and the Planck-Chandra legacy led by Christine found that the majority of the galaxy clusters are still being disturbed and still creating materials from the filaments. And in this accretion processes, there are two features I would like to highlight. The first one is the cold front, as shown in this Chandra image of this cluster. And this cold front is formed very similar to what we know in the climate. Is when you have a dense cold gas moving in a very hot diffuse environment, and we could observe a very sharp front. And the pressure between those two medium are in equilibrium. And another feature I would like to highlight is in the downstream of those infalling galaxies or groups is their stripped tail. As you can see, the top one is a galaxy group in the southern sky centered on NGC 1407, and NGC 1400 is the second brightest galaxy falling through the intragroup medium. And you can see there's a very beautiful tail trailing behind. And this bottom image is another example, NGC 4472. It is a group falling into the Virgo cluster, and it's just reached the virial radius of the Virgo cluster. We already start to see that it has the stripped tail. And such galaxy infalling processes are not only important in the cluster formation and structure formation aspects. It is also important for us to study plasma physics. And for example, this left image is a galaxy group highlighted in the red square. It is falling into the intercluster medium of this cluster, and this is the longest stripped tail has been reported so far, up to 800 kiloparsec. And this right image is my recent work. And it is a galaxy cluster, have 2 BCGs, so it is similar to the Coma cluster, but much smaller. And we found that there is a region indicated by this cross. It is a cold region with metal-enriched hot gas. And this cold region is displaced from either galaxies. And the survival of those cold regions in the hot intracluster medium could give us very important implications on the conduction efficiency in the intracluster medium. And so when it comes to the observation of Kelvin-Helmholtz instabilities, it requires much deeper exposure than those studies. And it has to be done with Chandra because we need to really observe the details of substructures. And there is a growing number of studies already start to work on this. For example, this is the super deep Chandra exposure of the Centaurus cluster at the center of this cluster. And you can see those wiggling ridges at this front. And this could be KH instabilities, but there are also many degenerate explanations because this is at the center of a cluster and has very active AGN outbursts. And there's a lot of sloshing things. So the explanations is not very simple. What we need is a clean case. So this is what I'm going to talk about today is the Fornax cluster in the southern sky, and this is optical image. And this bright galaxy is the center of this cluster. It's called NGC 1399. It's an elliptical galaxy. And so here is an X-ray image of this cluster. And so we are going to focus on this NGC 1404. It is falling into the central region of NGC 13 of this cluster. And so have a closer look is that so this NGC 1404 it has a cold, dense interstellar medium. It is interacting with the surrounding diffuse hot cluster gas. And the reason I call it a very clean case, it is because this galaxy doesn't have very strong active aging outburst. And it hasn't been interacted with any other galaxies for a while. So its explanation would be much simpler. And then this, the Fornax cluster has been, because it's very nearby, within 20 megaparsec away from us. So it has been a favorite of many generations of X-ray satellites. So here I highlighted some. And I want to point out my race work in 2005 is a very classical one because it kind of sets up the whole picture of this infalling galaxy, that it has a very sharp upstream edge and also has a extended stripped gas trailing behind. And so nobody could step into the same river twice, but we can observe the same galaxy twice. And so here I'm presenting new observations of this galaxy. Ralph is a PI of most of the new observations. And so as it all adds up to 670 kilosecond, very deep Chandra exposure. And this galaxy is very nearby. And Chandra has the best spatial resolution. And the exposure is deep, so it allows us to reach the spatial resolution has never been achieved before. And so to first I want to set up this, the picture is to try to constrain the motion of the galaxy. And so here we derived a pressure jump from the inside of the galaxy to compared to the frame stream. And here I showed the pressure jump as a function of this theta, the azimuthal variation. And this pressure distribution, it depends on the motion of the galaxy, and also depends on the inclination angle of the galaxy. And so we can solve this equation based on the Bernoulli equation and the jump conditions. And so we found the best fit of an inclination angle of 35 degrees. So this galaxy is not moving in the plane of sky. It is moving away from us slightly. And it is moving at a supersonic velocity of a Mach number of 1.3. So within this picture, and now let's start to move to study this galaxy. First, let's have a look at its upstream front. Here we derived the surface brightness distribution from this galaxy NGC 1404 to the center of the cluster. And there is a very sharp edge at the front of the galaxy. And now let's zoom into this edge. Is that here we found a bumpy feature right outside the boundary of this galaxy. And what is the nature of this feature? We derived the temperature profile across this edge. And the red profile is derived with local background. So it tells us the temperature of anything with enhancement to surface brightness, such as the galaxy itself and this bump feature. And we can see that this bump feature has almost the same temperature, as cold as the galaxy itself, and much cooler than the cluster gas. So it is most likely to be some galaxy gas sticking out of the galaxy, and instead of the fluctuations of the intracluster medium. And remember I mentioned before that we think this galaxy is most likely to have an inclination angle of 35 degrees. So this front we observe here is not really the stagnation point of this galaxy. It is on the side. And so far we think the most plausible explanation of this bump feature is this is the KHI rose developed on the side of the galaxy. And as you can see here, this is a simulation work and how we can observe the KHI rose based on the inclination angle. So when it's more easy to observe it at the front in projection when there is a larger inclination like this.
Is the scale there in arcseconds, please?
Which one? I mean, the top is
No,
kilo.
for the galaxy there, for the image.
Oh, the radius is in.
It's okay, if you look afterwards.
Oh,
I'm wondering how big it is.
okay. And
I know where the edge is, you can see where it drops there, and the bottom scale, 105 seconds.
oh yeah, and the top is PC. And so the KHI rose we expected to be bigger even downstream of the galaxy because the shear flow velocity is increasing. We do see some possible bigger rows on the side, such as this extended front. And also there is a boxy front on the other side, down the stream. And this has been observed in other clusters too. For example, in this ABL 496, and there is a very sharp boxy front. It has been reproduced in simulation, and it is caused by the KHI rows combined with some projection effect. And so now we know that we are more likely to, we're likely to find the KHI rows in this system. And now let's compare it to simulation. Simulation predicts that the viscosity would suppress KHI rows. And for example, the left image is in the scenario where the velocity is very low, and we can see those patchy features developed on the side. While the right image is when the viscosity is very high, the edges is very smooth. And the fact we observed the KHI rows on a scale of 200 parsec strongly prefers the low viscosity scenario. And we can even put quantitative constraints on the viscosity. We think it's should be smaller than 5%, 0.5% Spitzer value. And another factor which could also suppress KHI rose, that is the magnetic field. This is a simulation of the sloshing front in the center of clusters. And as shown on the left, when the magnetic field is weak enough, KHI rows start to appear. While when the magnetic field is strong enough, we should expect those smooth edges. And again, in this case, also at the front of those infalling galaxies, the magnetic field should be even stronger because due to the strapping of cluster magnetic field, and the magnetic field will stressed out, and to form a stronger magnetic field than the magnetic field in the free stream. For example, this is the cold front in this cluster, and the edges is so sharp, requires a strong magnetic field to preserve this edge. And in our case, we observed the presence of KHI rows imply that the magnetic field shouldn't be too strong. And we can put the upper limit on the magnetic field is 5 microgaussian. And this is an independent measurement of the magnetic field using rotation measurement for exactly the same cluster. And so we can see that if this is the magnetic field of the free stream, then the magnetic field may be amplified by a factor of less than 20 in this case. Another information we can take from this upfront edge is that it is consistent with a super small discontinuity, smaller than the spatial resolution of our study. And we found that it is actually smaller than the mean free path, which means the electron diffusion has been suppressed in this case. And the magnetic field could suppress the electron diffusion. Unlike KHI rows, it only takes a little bit of magnetic field to suppress diffusion. And so this could at least give us a lower limit. And now let's move to the downstream stripped tail. Even considering the projection effect, the length of this stripped tail is very short, given how big this bright, this elliptical galaxy is. And again, we can compare it to the simulation. In the case of high viscosity, we expect to observe very long tail, while in the case of low viscosity, the tail will be very short. So it qualitatively supports the case of low viscosity. And here we derived the two-dimensional temperature distribution of this system, and the contour is the X-ray image. So we can see that the surrounding ICM has a temperature of about 1.5 keV, while the galaxy itself, the rimmed core, is very cool with a temperature of about 0.6 keV. And here is the temperature of the stripped tail. We can see that it is hotter than the rimmed core and still cooler than the surrounding cluster gas. So it is a sign of mixing in this stripped tail. And again, let's compare it to the simulation. And we can see that in the case of high viscosity, we expect to observe cool tail. And in the case of low viscosity, the tail could be efficiently mixed with the ICM. So again, it is qualitatively supports the case of low viscosity. And so as a summary, we presented the general study of nearby early type galaxy NGC 1400. And we determined that it is falling at an inclination angle of 35 degrees at a supersonic velocity. And its stripped tail is very short and turbulent and mixed. And it has, we found even evidence of KHI rows on a scale of 200 parsec. And the electron diffusion seemed to be suppressed at the up edge front. And those two facts lead us to a conclusion that the viscosity should be very low in this intercluster medium. And we put the upper limit on the viscosity. And the other two facts allow us to put the upper limit and lower limit on the strength of the magnetic field. And so what's coming up next is we are going to have tailored simulation just for this galaxy to do an apple-to-apple comparison. And so this study showed the importance of studying the astroplasma physics using X-ray observations of galaxy clusters. Thank you.
Questions for you, anyone? Yes.
Temperature map is very nice. I'm just wondering whether you have made a abundance map as well.
I do. It's not here, and the galaxy has a higher abundance, almost twice as high as the surrounding ICM. And for the tail, we can't do the abundance of those individual regions. We have to extract the whole region of the whole tail to measure abundance. And we got a very low abundance, but this is likely to be the iron bias because it has mixed temperature of different gas. So we try to do the two temperature components, but we can't constrain the abundance. Then we kind of fix the ratio, we got a higher abundance.
Did you also look for a bow shock because you said supersonic?
Yeah, that's right. So
Where do you expect it to be roughly, or is it outside of the field?
the thing is that, so there is a inclination angle of this infalling or merging. So when inclination angle is really large, due to projection effect, we actually usually don't see the bow shock. And however, in this case, the mark cone, it is larger than 35 degrees. So we should still kind of see this bow shock somewhere. And actually, at this Mach number, we expect to detect the shock cluster gas of a temperature of about 2 keV. So it's not much higher than the ICM temperature. So we may see some 2 keV gas here as sort of shown here, but I don't know how much is due to the fluctuation of the ICM itself. And you can see the uncertainty is very large. And they are not shown in the temperature map because the thinning is very large, so it may average out the temperature.
Other questions? So in that case, let's thank you.
Our next speaker is Dr. Jeff McClintock. Jeff is a senior astrophysicist at the Center for Astrophysics. He got his bachelor's degree from Stanford University in 1964, and he got his PhD degree from MIT in 1969. After that, he has been a research scientist at MIT. He joined the Center for Astrophysics in 1985, and he won Rossi Prize at AAS in 2010. And he is an expert on the X-ray binaries containing a black hole. And today he's going to talk to us about the spinning of stellar black holes.
Oh, yes. So in this short amount of time, I'm going to just be talking about our work. I hope everyone understands there's a lot of other work going on in this subject. So stellar black holes are very nice. They allow us to see in a very short time, a human time scale, what black holes can do. And since everything scales with mass, this tells us about cosmologically important supermassive black holes and how they operate, because the time scales and size scales just scale with mass. It's sort of like comparing a volcano. These things are on a human time scale, like a year or something, they go off. And instead of millions of years, a glacial kind of thing you get with supermassive black holes. So that's why I call them lively, and I'll try to make it clear why I call them lively. So this is my outline, a little introduction. Then I'm going to talk about the continuum-fitting method of measuring the spin, which is what we've been doing the last 10 years. Then I'm going to talk about 3 applications of these results, and then describe very, very briefly the iron line method, and if I get to it, what excites us right now, the RXTE work that we're doing. So this is, there's about 50 of these stellar mass black holes that are in X-ray binary systems. This is sketched to scale of 23 of these systems. The scale is indicated up here, sun size right there. And these are binary systems. The star is accurately drawn in Roche geometry, and you can see this little area here where the stream can go over into the disk, and the black hole's down here in the center of the disk. And the difference in size between these hasn't much to do with mass. The black holes are all about 10 solar masses. The difference in size is the difference in orbital period. So the big one here is like 33-day period, and the littlest one down here is about a 4-hour period. So that's what sets the size scale of these systems. Now there's 2 classes of systems, and this is very important for this talk because I'll come back to it a number of times. So I'll try to make this clear. There's 2 classes of systems that have been described as 2 classes for a very long time, but the evidence that we have from mass and spin measurements differentiates this class once more, as I'll show later. So there's the persistent systems up here. The most famous that you would know is Cygnus X1, and there's one in M33 and one in the LMC. They're pretty rare. And then there's these transient systems that go off for a year or so. So the transient systems are, in a sense, the more interesting, because in 1 year, they do everything that a black hole can do, the full repertoire, from 10 to the minus 8 of Eddington, 10 to the minus 9 of Eddington, up to Eddington, and then back down again. So they show you everything, whereas the persistent systems just keep going. So here's a sketch to indicate what these 2 systems look like. So here's Cygnus X1, a picture of it, and here's your O supergiant star, 30 solar masses or so, and here's your accretion disk, and the black hole's down in the center of that accretion disk. And so there's a wind coming out from this O star, and it just gets vacuumed up by the black hole, and there's some angular momentum, so it goes into this little disk around the black hole. But it's persistent because the wind is there all the time. But these systems, the transient systems, have a lake-type star, and there's an accretion stream. They fill their Roche lobe, and the material flows over in and strikes the accretion disk, and the black hole is here at the center. These are transient. They're only on for about a year, and then they go into deep quiescence. And I'm going to spend a fair amount of time talking about these objects. So the next slide shows a light curve, an X-ray light curve of one of these objects. So here's your intensity in X-rays, 2 to 12 keV, and here's a time, about a year, and here's the X-ray light curve. And what you see is that they peak at around the Eddington luminosity when they're really doing a large outburst. And at that time, a jet is launched, which I'm going to talk about later, a ballistic jet. And then later on, they're very thermal. And there's just a thermal emission from the accretion disk. And the disk just cools. That's this part. But up here, it's Comptonized and a very complex spectrum. So here's where we get the data to measure the spins for continuum fitting, where the disk, just the accretion disk, dominates the total emission. Here's where we get the data for measuring the iron line. As I'll describe later, you need a significantly Comptonized spectrum, and I'll describe what I mean by that a little later. So this is a typical X-ray light curve. Now the next slide is kind of nice, because what the next slide is going to do is it's going to walk you around this light curve and show you how the spectrum changes as this thing evolves over this time scale of a year. So this is a very nice slide that Tommaso Belloni sent me, and what you're going to see, I'll stop it right there, is this is called a hardness intensity diagram. So if you get into this business, you've got to learn this. So the top part here, this is intensity. This is RXTE, PCA, proportional count rate. And here is hardness, X-ray hardness. What this is the ratio of counts in the PCA detector, say 10 to 20 kilovolts, divided by the counts in 2 to 10 kilovolts. So it's a hardness measure. And the spectrum's very hard over here at this early time. So in this animation, 1 second is a week in observing time. 1 second is a week, and 1 minute is the entire evolution over a period of 1 year. So you can now get a feel, and so the top part up here is the hardness intensity diagram, because this is in intensity and this is hardness. But look, there's a little extra here, percent RMS. So this is timing information. So this tells you how strongly the X-rays are flickering. So this percent RMS is the power density spectrum from 0.1 hertz to 10 hertz, integrated average. It's just the flicker noise at 1 second is really what it is. And it starts out over here at about 40%. And then you'll see as it gets over to the soft state, it gets down to just a percent or two. So that's very interesting too. So both of these things are going to happen, I hope. Right. Okay, so it's in its hard, you see it here, it was in quiescence, and it went up in its hard state. Oh, when you see that star there, that's when it ejected the ballistic jet that I'm going to show you a little later. And now it's over into the soft region. And now it's what's called the steep power loss state, or the very high state, if you want the terminologies and so forth. And it's up there and languishes up there for a long time, and then eventually it's going to come back down. You'll see how this timing noise, the flicker noise, was 40% flickering at the beginning and very low flickering here, down in the vicinity of 1%. This is where we do the continuum fitting. This is where the disk is dominant. And this region in here, and over in the hard part too, is where you can do the iron line method of measuring spin. So the thing now is retracing itself back to quiescence, which can be 10 to the minus 9 of the Eddington luminosity. So there, in 1 minute, of course 1 year, you just saw what a supermassive black hole would do in millions of years, meaning you would never see it doing it in millions of years. So the value of these things is that you can get it all very fast. Now this slide here is a divider slide to move on to the continuum fitting method. And Ramesh and I have co-led this effort for the last 10 years. And Ramesh and I started actually with Rebecca Shaffey down here, a physics graduate student from Strominger's group. Was working on string theory and wandered up here because she was dazed from string theory, and she started working with us on this, and it was wonderful that she did. She was just a terrific student. So Ramesh and I got this going, and Jack Steiner, who's was a student here and then a Hubble fellow and now an Einstein fellow down at MIT, just took it to a completely another level. Okay, so that's what students do, of course. And so this is the people, and if you want to know about this, this is our most recent review article in Space Science Reviews. So the idea is that one has a thermal accretion disk, and that disk terminates at the ISCO, at the innermost stable circular orbit. And inside the ISCO, it's dark, because the material, once it reaches the ISCO, plunges in a millisecond to the event horizon, so fast that it can't radiate. So there's this dark hole, this dark region here, and then there's this hot thermal disk out here. And what we're measuring is we're measuring the radius of the ISCO. So here it is, the radius of the ISCO in dimensionless units, C equals G equals 1. So this is the radius of the ISCO, and this is the spin of the black hole. So this is a famous thing by Bardeen, 1972. The spin of the black hole, which is proportional to the angular momentum of the black hole, which is limited to be in these dimensionless units, -1 to +1. And the radius can go from 0 to 9. So that's the range. So it's a very large range of radius that we measure. And now you ask, how do we measure this? Because these systems are, after all, 10 solar mass black holes. So they're 1,000,000 times smaller than Sagittarius A star, which is really hard to resolve, as we know. So the answer is, of course, you don't resolve it. What you do is what you would do if you wanted to measure the radius of a star. So you measure the radius of a star, you measure the flux from the star, you measure the temperature from the star, and if someone gives you a distance estimate from parallax or something, then you can very trivially estimate the radius of the star. And that's what we're doing. We're taking X-ray flux and X-ray temperature, and we're determining the radius of this ISCO. But we need more than you'd need for the star. We need more than just the distance d. We also need the inclination, because you're dealing with luminosity here. So you need the inclination of the disk, you need the mass of the black hole, because you get this ISCO radius in centimeters, then you have to scale it by the mass of the black hole into dimensionless units, as I had on that previous plot. And then you need a model of the disk flux as a function of radius, because it's not a uniform emitter like a star. So for that, we use the model of Novikov and Thorne. So this is flux, this is radius, and if you look, for example, at the 0 spin black hole, you see that the emission goes completely to 0 at 6m, at the ISCO radius. And as they spin more rapidly, these are four black holes, all identical, all at the same inclination, all at the same mass accretion rate, all at the same mass. And the only difference is their spin parameter. As the spin parameter rises, this ISCO radius goes in, as you can see, and that's what we're measuring. And of course, as the spin goes up, they become much, much more efficient. This is 30% efficient in terms of converting infalling rest mass into energy, and this is 6% efficient. So we use the model of Novikov and Thorne, but how good is that model? Well, that was a major accomplishment of Ramesh and his group over the years here to measure, to simulate with GRMHD simulations, thin accretion disks, and to determine that the key assumption of the Novikov-Thorne analytic model is okay. And that key assumption is that the dissipation at the ISCO is 0, that there's no torques at the ISCO. The material, once it reaches the ISCO, just falls freely in. And in fact, the solid lines here are the Novikov-Thorne, and there is some emission from inside the ISCO. This is the GRMHD, the dashed line here. There's some emission from inside the ISCO, but it's a small effect. It's smaller than our uncertainties in our measurements of mass, inclination, and distance, which are the key uncertainties in measuring the spin. So the answer is we use the Novikov-Thorne model. If we ever can do better in measuring mass, inclination, and distance, then we start to use these GRMHD simulations. So this just shows a really nice spectrum for continuum fitting, the spectrum of LMCX3. And you can see that the thermal disk component is about 2 orders of magnitudes above the Compton component, which I'll describe in a moment. And so it's totally dominated by the thermal disk emission. This is ideal for continuum fitting, because it doesn't matter when you want to model this little component out. 99% of the emission is in the disk component. So this is a very nice piece of work that Jack Steiner did, where he took 750 observations, most of them from RXTE, those are the red dots. And here's the luminosity of the accretion disk over 26 years. And what you see is it's highly variable, and this is the number of different missions here, but RXTE are the red dots. And if you calculate the inner radius divided by m here, then if you just say, look at the RXTE data alone, it's stable to 2%. So this shows that there's a constant inner disk radius in these systems. And it's a strong observational piece of evidence that the continuum fitting method is a valid approach to measuring spin. And then the theoretical curves that I showed you earlier show that that radius is really the ISCO radius. So here's our spin and mass data. So these are complete descriptions of these 11 black holes, because of these 11 black holes for which we have both mass and spin data. because that, according to the O'Hare theorem, completely defines them. So we have these masses and these spins, and we have them for the two groups. And now what I want to do is to use these data and apply them to three results. I'm not going to give you all the details. So these are applications of this spin and mass data. And the first one is just to show this table and to point out that for the persistent systems, true, we only have 3 of them, but that their spins are all high and that their masses are all relatively high. And for the transient systems, the spins range all the way from essentially 0 to very high value. And the masses are consistently lower, or generally lower, than these up here. And this is a result from Ozell et al. 2010 for a larger sample of masses of transient systems, that their masses are about 8 solar masses and are less. So this differentiates these two classes of systems. This one with the wind-fed O supergiant massive companions, and these with the generally very low mass companions and accretion overflow, Roche overflow systems. So that's one, just the differentiation between the two classes of systems. And here's another application of these spin data. So you can ask, how did these black holes get their spin? And for the systems up here, these systems are not older than 10 million years. They're a few million years because the O supergiant stars were just dust before that. They were just interstellar medium. So they're very young systems. And you can ask, to get these spins, there's 2 ways to do it. One way is they were born with these spins, or the other way is that they were torqued up over time. And the answer is there isn't enough time to torque these black holes up to these spins in the lifetimes of these systems. If they were radiating at the Eddington limit, and they're not, they're radiating presently at 10%, but if they were radiating at the Eddington limit, it would take more than 100 million years for each of these systems to reach these spins. So we argue on that basis that these are natal spins, that these are the spins that the black hole, it was imparted by its progenitor star. And then for these systems down here, you know something? Oh, no, it's up here. I thought maybe I'd left the citation off. No, it's up here. So there's a very nice paper by Tassos Fragos, and I provided observational data about these systems. And he makes a very beautiful argument, and it's very detailed with a MESA code and all kinds of evolutionary arguments and so forth, that what happens here is that in these systems, the progenitor of the black hole, at the time the black hole forms, is not rotating, or effectively rotating very slowly. And that the spins that these black holes have are the result of accretion torques acting over 1 billion years, because these systems with low mass companions are generally ancient. So over very long times, these spins, in the argument here, is that these spins were accrued by accretion torques over time, and that this black hole, when it formed, had effectively 0 spin. So it's a very different picture for these two. And one corollary of this is that if you take a system with a very high spin, like 1915, to get to that spin by accretion torques means that the black hole had to essentially double its mass. And what this means is that Tassos, in this paper, takes each one of these black holes and goes back in time and says, what was its birth mass? So, as I said in the previous slide, or a couple slides back, that these are less massive already, these transients. They're less massive still, even more, when they're born, because they've accreted a lot of mass to produce these spins. And as I say, in the case of an extreme case like this, the mass is doubled. So it's gone from 6 to 12 solar masses in this picture. And then the third application is to ballistic jets. So this shows GRS 1915, which is the most famous microquasar, and the X-ray source is right here at the cross. And these are 6 images in a loop that's being shown in a loop of plasma blobs from VLA observations, radio observations, of plasma blobs moving out on the plane of the sky over a period of a month to about an arc second. And these blobs are being shot out at about 90% the speed of light, at Lorentz factor 2 or so. And so this is, and many of these systems do this, and this is what earned them the name microquasars that Felix Mirabel gave them, Mirabel and Rodriguez. So this is the slide I showed you earlier of a light curve of one of these systems. And as I wrote earlier, this is where the jets are launched when they reach Eddington. And here I've added the radio data for this source. And what you see is that when the X-ray source goes to Eddington, there's a large spike in the radio emission. So what Ramesh and I did in 2012 is to make the argument, theoretically, that this is a reasonable proxy for the power of this ballistic jet. That is, the peak radio luminosity here is a good proxy for the power of the jet. And using that argument, one can then calculate the jet power, which is effectively this peak radio luminosity. And then when we have these spins we've been measuring, the spins are pasted up here, but really here we use the observational quantity, which is our measurement of the inner disk radius. So when you do this, these are the data right here, these data points. And the story was better before Mark Reed helped us, because what happened was this point was up on the curve. This is the way we published it. But what's happened is it's moved down because Mark insists, just from trigonometry and VLBA work, that the distance is shorter than we thought it was. So this point moved down. But I should tell you that the solid curve here is the prediction of the Blanford-Zanajek 1977 model, which is the model that describes how black hole spin can power jets directly. And the jet power in this picture is proportional to the angular momentum, the angular velocity of the horizon of the black hole squared. So the only fit parameter here is the normalization of that curve. Now, the situation got worse again because we did another source, Nova Muskie, and we have a point here. So the evidence isn't as clear as it was. This point is formally 1.9 sigma off this curve. Okay, so this will, I think, this is a suggestion at this point. It's the first evidence of this kind because you need measurements of spin that you believe to make this kind of an argument. So the answer is that in the next year, I'm very excited because Meerkat, which is the forerunner of the SKA, is going to come online. And Meerkat is going to monitor these these transients and get these radio light curves because it's the quality of the radio data in the literature that has really hampered us in doing this work. So that's the third application. So now I want to turn quickly to the other method of measuring spin, which is extremely important because this is the method that applies to active galactic nuclei, to supermassive black holes. And I'm just going to say, I'm not going to say anything about Laura Brenneman's work, but she is a leader in this field. But she works on the AGN, but I'm going to be talking mostly about the stellar mass black holes here. So this is also called reflection spectroscopy. So what is this? So I'll remind you again, this is the very simple situation that we have when we're doing continuum fitting. We're just looking at the thermal emission from the disk, this thermal component. And then, of course, we need these inputs of mass, inclination, and distance. Those are hard to come by. But when you do the iron line method, it gets more complicated. So this is the Comptonized stuff I was talking about. So here's the point. One has thermal emission from the disk, the red arrows, scattering in a corona about which geometry and so forth and properties. One doesn't know a lot about it at all. And then one gets Compton upscattered hard photons. That's the blue power law. That's the blue power law here. And then that power law, some of it you see directly in the spectrum, and some of it goes back and strikes the disk and produces this so-called reflection spectrum, which is this complicated spectrum which is reprocessing fluorescent lines and other features that are reprocessed emission in the accretion disk. And the important point is actually the iron line right here, because that's the one that's in the observable band, free of interstellar problems and so forth. And the iron line gets relativistically broadened in the disk. And the two parts of the iron line that are important, so this is drawn for 40-degree inclination. And here are two models of the iron line by Javier Garcia, who's a postdoc here, who has got the most advanced models of this reflection spectroscopy now. And you see that on the red wing, you can differentiate if you model this profile between, you can estimate the spin of the black hole. And on the blue wing, you can estimate the inclination of the disk, because the Doppler effects are going to be greater. They're zero if it's face on, and they're maximum if it's edge on. So you can estimate, so this is a 6.4 kV line that's been, you can see blue shifted up to here. So what we've been doing, and I just want to tell you in the last couple of minutes, the most exciting thing in the last couple of years has been working with Jack Steiner and Javier Garcia. Javier Garcia is leading the work on RXTE data. Can you believe it? RXTE data. RXTE is gone. It's in the archive, right? It's 2012 was the finishing year, but it's a big archive of data. And there's 29 black holes that were observed daily, like that one I showed you early on. There's about 500 observations each. There's 10 million counts per spectrum. Here's the PCA. And what we did is very exciting, very simple, is we took what we did is we reduced the systematics in the detector by an order of magnitude. And why did we do it? We did it because we wanted to do reflection spectroscopy. We wanted to look at the iron line and so forth. If you want to look at faint features, you better have something better than the response matrix they had for the PCA. So we took all the Crab spectra there are for the mission, and we fitted each individually to a power law, got the residuals, added up all the residuals for the mission, and you get this curve here, which is, if you assume that the Crab is a featureless synchrotron spectrum, this is the hair, the noise, the garbage that's been in the response matrix for the last 20 years. So we take this out. We calibrate this out. And we have shown that this is stable over the entire lifetime of the mission. So we use this to correct the data to get to 0.1% system. So this is the difference between what people had been doing, where you might have 1 million counts in a channel, in an energy channel around the iron line or something, and because you had 1% systematics, you only could use 10,000 of those million counts. Now we can use the whole million, because square root of a million is 0.1%, square root of 10,000 is 1%. So this is a cartoon that we stuck in an NSF proposal recently to just indicate the kinds of precision measurements we're making. And this shows, for the same source that I showed dancing around the curve earlier, what happens as the luminosity of the disk in the hard state drops from 17% of Eddington to 2% of Eddington. And what happens is the inner edge of the accretion disk moves out, and we have a very precise measurement of this, and the coronal temperature increases by about an order of magnitude. So we have 11 continuum-fitting measurements, and this is a very robust method. I've described 3 applications of these data, a distinction between these 2 classes of black holes, the natal spins for the wind-fed systems, persistent systems, and the accretion torques producing the spins in the transient systems. Describe this evidence for how jets are powered by black hole spin energy. And then I've very briefly mentioned this achievement here. And we're very keen on pursuing this very heavily with focus on the iron K line and edge. And at the bottom here, I just added this triad thing because it just came to me that, the event horizon, so there's no straight path to observing black holes and getting, and advancing this field. There's no simple way, and you can't put all your money on one bet. It just doesn't make sense. You've got to try. So, what, I just hit the wrong button, I see. Okay, can I do this without my glasses? I think so. Yeah. So this is to indicate that there's three good ways to go. And one way is the Event Horizon Telescope. Obviously, imaging the black hole is an amazing achievement. But, you know, it is limited to two starved black holes, okay? So it's not a universal knowledge of black holes that you're going to get from this. And then LIGO Virgo, what we're going to hear tomorrow, I hope, something really big here. And this is profound. I mean, you're going to see what vacuum black holes do. And you're going to really get as close to testing general relativity probably as you can. It's an amazing achievement. This started in the 1970s with Ray Weiss down the street here. I bet he's already getting his tickets to Sweden. But seriously, it's like, this is an amazing thing. But let's not forget accreting black holes, which is what I'm talking about, whether supermassive or stellar mass, because they show us how black holes interact with matter in the universe. And they're the ones that are cosmologically significant in terms of sculpting galaxies, setting the large-scale structure, and so forth. And one can learn a lot from this avenue as well. So, with that, I stop.
Any questions for Jess?
Jeff, I'm curious about your opinion on the ability of continuum fitting to assess the spins of intermediate mass black holes. There have now been a couple different claims in the literature of people applying your methods
Yes.
to theoretically these intermediate mass systems, and I'm wondering what you think of the robustness of the results.
Right. So there have been two papers that I'm aware of that where supermassive black holes have been attempted to use the continuum fitting method. And some limitations of this are that one generally doesn't know the inclination. And that's a big problem, because if you don't know the inclination or have a good estimate of it, then that is huge latitude in terms of estimate of the spin you're going to get. Another big problem is that the emission you're talking about that you want to measure is this continuum emission, the blue bump in the UV or EUV or whatever, and it's very hard to observe it and get a clean measurement. So there are very few AGN for which you can hope to get some kind of an estimate, and then it's always polluted by the environment of the AGN and everything. So my opinion of the two papers that I've read is that I'm not excited about working on it myself. I mean, it's just very, very uncertain and very hard. But I would love to be proved wrong.
Do I have another question? Oh, well, he got one, so I don't have to pick one. Jeff, I have to ask you how you define persistent, because if you look at the light curves of GRS 1915, SIG-X1, LMC-X1, over 16 years with RXTE and even beyond, GRS 1915 is persistent. It never goes into outburst. And if you look at your system of persistent versus transient, it's up there on top. It has spin above 0.8. It has mass above 10. It fits in with the persistent. So why are you putting it in a transient?
So
That's one of your 4 points that
Yes.
works.
So GRS 1915 is this very large system with a 33-day period. It has a K giant secondary that's about 3/4 of a solar mass. It doesn't have a 30 solar mass O supergiant star. So right there, I differentiate it. Okay, but
Why don't you call that your different? Why don't you say a massive secondary
But also-
as opposed to transient and persistent? Because it's persistent.
no, I mean, you know, any classification scheme, I'm not going to debate the classification scheme, but I would say that GRS 1915 it was not even an X-ray source in Uhuru days or until 1992 or whatever it was when it suddenly came on. And because the disk is so large, there have been papers written that it will turn off like the other transients, but it takes a very long time to clean out a large disk. But I'm just talking speculation. But really, the basis is really that it is persistent for human beings for 15 years or something, but that's not what I'm talking about. I'm talking about persistent throughout the lifetime of the system, and I do not think it qualifies. It was dead off, you know, until the GRS, the GRS satellite found it. what is it, GRS? What is that? Gamma ray? Granat sigma. Granat. Sorry, yeah, excuse me. So anyway, I see them as different.
Jeff, here, Jeff.
Yes. Oh.
Is a high mass X-ray binary persistent and low mass is a transient generally?
Generally, yeah.
Any exception of that?
Well, we were just talking about 1915, which has been on for the last 20 years or something. Yeah, I mean, no, I don't want to debate this anymore. Please, we can talk about it privately. I mean, I said all I need to say, I think.
Regarding your use of the crab on an RXTE
Yeah.
calibrate, we know that the crab does vary from time to time. Did you take, I mean slightly, did you take this into account, or was it such a low level it wouldn't have any effect on what you did?
So we're letting we're fitting each of the individual 417 spectra, and so the normalization might vary a little bit, possibly even the power law, but we're taking all that out, and all we're looking at in the end is assuming that we're working with 417 featureless spectra, we have this spectrum of summed residuals, and that thing is pretty immune to any variation. We argue that in the paper.
When you talk about the persistent sources, you seem to be implying that if it's fed at a steady rate, it's persistent, and otherwise it's transient. So do you think that there's no role for disk instabilities?
Well, that's interesting. So disk instabilities, you mean in a persistent system, would...
It sounds like you're kind of implying that in any system you don't need disk instabilities, that in the others you are increasing the mass transfer rate from the system.
No, I'm sorry. No, if I didn't really talk about, how the transients go through their cycle, but the general picture is the disk instability model that applies to CVs and so forth, where the disk builds up over decades, and then a thermal instability sets in, and the material flows to the black hole, and the whole disk goes unstable. That's a standard thing for the transients. For the persistent systems, you were raising in my mind the interesting question of, well, maybe why shouldn't those disks be unstable? But I think the answer is in a paper by von Paradise a long time ago, where he describes systems where the disk is irradiated sufficiently, it stabilizes it. And I would imagine that maybe in these persistent systems, the UV and so forth, keeps the disk in a state where it doesn't go into this instability. But I never really thought about it. Yeah.
Okay, let's see.
Thank you.
And it seems to follow on sort of obviously from what you said. So it sounds like there are now two different formation mechanisms for the transient sources of resistance. So for the transient sources, would you say that that's indication where you have something like a white dwarf